I put lots of reading material, like also video. We have both MATLAB and LabVIEW. I'm not sure you already read it or not. Because today will be the last chance for our communication before the stage 2. So stage 2, we have mainly dealing with non-stationary signal. Yeah. So what's non-stationary signal? Do you have any idea? So what's the difference between stationary and non-stationary signal? Hi, Julio. Hello. Yep. Probably the communication is not that good. So today I will, because last week I discussed about continuous wavelet. For the continuous wavelet, the main problem is like the calculation cost is too much. So we need to lots of calculations. It's not that fast, not convenient. So the mathematician developed the discrete time wavelet. So like fast Fourier transform. You know, like before fast Fourier transform being developed, it is very hard to do the even just do Fourier transform for a signal. And after the fast FFT developed, and then the filter, the Fourier transform becomes very feasible. So for the discrete time wavelet is the same thing, similar issue. Maybe we need to wait for some student to come. And you three are all is from overseas, right? Hello. Probably I share my screen. We start to discuss about today's lecture. Have you seen these slides? Because this is a theoretically discuss about discrete time wavelet. So the discrete time wavelet, the main thing is they can denoise. So it's much better than the FFT. I mean FIR and IR filter. So they are more powerful. They can deal with non-stationary signal. And also DWT, discrete time wavelet, can do the compression of large amounts of data. So they can even for the or that mean tau is a job as well. Hai Mingnan, Julio, how maybe have some issue. So I'm just want to get your feedback. Have you read the document I put in the room? Do you have any questions, any problems? Because if I just discuss, if you no feedback, it's very hard for me to understand where you are clear, where you're not clear. Hi Tao. Hi Shantao. So how is your group? Guoqiang? Fuqiang? I cannot hear. Quite strange. We cannot hear each other. Hello, can you hear me? Okay, if everyone can hear me, and then I continue. I think we need to continue our discussion. So basically, I want to ask you your feedback about all the material I put in the website. Especially, I want to know your progress of your stage 2. I know Shantao and Mingnan is in the same group. Julia is in group 3, right? I just want to know every group are going well or not. So first we look at this slide talking about discrete time Fourier transform, discrete time wavelet. So this is they basically in the stage 1 we already learned. Do you still remember we learned 2 kinds of filter? So this kind of filter is one is called FIR and another is IIR filter. Actually, implement discrete time wavelet, we only use one of the filter, kind of filter. Can you guess? We use FIR or IIR filter. Can anyone still remember which filter is more stable? Is IIR filter or FIR filter? Actually, IIR filter sometimes will be unstable because they have poles. If the pole is outside the unit circle, and then the filter will be unstable. We also have a FIR filter. FIR filter doesn't have any poles. They only have zeros. So IIR filter, the FIR filter always stable. So for the wavelet, for the discrete time wavelet, actually we only use FIR filter because FIR filter is more stable and also is can implement a linear phase. So for the this is the figure how to implement discrete time wavelet. So here you can see if the signal come from here, they have two filters. So it's the first level. So the first level is we have a high pass and a low pass filter. And then they all downsample after the filter, they downsample, and then the high pass, low pass again for the low here the above is low pass. So low pass is like approximation of the signal, and high pass you can treat as a noise. So this is the first level noise. So this is the structure, but they need to design a filter bank. So they use not only just one filter to implement the discrete time wavelet transform. They use 4 filter, construct a filter bank to do that. Let me look at the people's. So not many people join the lecture. Yeah. So we look at another material. Maybe it's more useful to let you to understand the. So this have a. So here is the here is the explanation for discrete time wavelet. So if there's signal, the first pass, there's a high pass and a low pass, and then the downsample, and then they do the low pass, high pass again. Yeah. You can see the after pass first level, low pass, this is high pass and the low pass. We normally call high pass is called detail. So that's a detail, actually it's noise. After low pass actually is approximation of the signal. So it's called the approximation. So after the first level of low pass and high pass, and then the low pass component will do the filter again. First pass a high pass and then pass a low pass. So the low pass one continue. So this one can called multi-scale analysis. So that's the name of multi-scale analysis. So this is the structure of DWT. And the very good thing is like we can use MATLAB to design the low pass and high pass filter. So this low pass and high pass filter is very important because you know, like it's not a normal low pass and high pass. You cannot design like I teach you in the first stage, design FIR filter, because I told you it's FIR filter. Because we need to implement the, you remember for the wavelet, we have one thing is like we can select different kind of wavelet. For example, maximum height, Dubash1, Dubash2, and also like Hara wavelet. So to implement the different wavelet, actually, what you can do, actually, you just design the filter coefficients. If the filter coefficient is different, they can implement a different wavelet. So this is a very amazing. So it's an amazing result. Mathematicians do a lot of work, beautiful work. So I use MATLAB to show you what's the coefficients for different wavelets. Probably we open one of the code. If we look at the DWT coefficient, so if I run this one, so we can see this one is they have. I remember I already taught for the discrete time wavelet transform. We normally need a bank of a filter. It's not only just one filter. We need the full filter. They need low pass, high pass. Another is another level, low pass, high pass, because they have a DWT and the inverse DWT. So they have a two stage. So this one they need a full low pass filter. Full FIR filter. So we look at the coefficient. You can see I mentioned before, the coefficients is related with the wavelet name. For example, you have different wavelet name, you have different coefficients. Here, I use a wavelet name is Dubash 25. That means they have 25 coefficients. If you look at this one, if I run, so this is the filter bank. You can see they have a full filter. They have a 4 filters for the Dubash. 2 is for decomposition. I told you like they have decomposition. That's a decompose the signal. This is a low pass. This is high pass, right? You can see their coefficients looks very strange, right? So actually, if you want to implement the Dubash wavelet, Dubash 25 wavelet, your filter coefficients should be like this. And here, another 2 filter is for the construction. Hi, Zhiqing. Hi, Zhiqing. Can you hear me?
Can you hear me?
Yeah, I can hear you.
Sorry, my net may be poor, and the Fuqiang tell me, his office has something emergency, so he will watch the record after the class.
Okay. So probably we we continue. I'm just wondering, like, because next week will be the demonstration. I'm a little worried about the progress. But anyway, we continue. Ming-Na is job as well. So this is because I cannot get the feedback from you. So this one is called a filter bank to implement discrete time Fourier transform, discrete time wavelet. So you can see this is for the amazing thing is like you just change the coefficients of the low pass and the filter and the high pass. You can implement a different wavelet decomposition. So this wavelet decomposition, this reconstruction. So I discussed the decomposition. I haven't discussed how to reconstruction. Now we look at different, for example, wavelet. So this wavelet is Dubash 25. We can use, for example, Dubash 10. And then you can have different shape. You can see they have different shape and the different lengths. If I use another one, for example, this one probably is more different. So if I use this one, right? And then you can see the coefficient. So this one is much different with the previous one, right? So but they still use full components, full filter to construct the filter bank to implement both wavelet decomposition and wavelet construction. This video is only talking about decomposition. Actually, if you want to reconstruct the original signal, what you can do? Actually, first you can, after level 4, what you can get is actually you can get D1, the detail level 1, and you can approximation, you can only get approximation 4, and the D4, D3, and the D2. So when you construct the signal first, you use these two components, construct A3. So this D4 and A4 use the construction filter. I already show you we have a decomposition filter and the construction filter. If you use a construction filter to do this signal and to do them together, you can recover A3. And then we construction filter again, use D3 and A3 as input, you can construct A2. And recursively, you can recover from A2 and D2, get A1. And then A1 and D1, after the filter, construction filter, you can get original signal. So that's the procedure. Now we look some example, like have you run some MATLAB code? For example, this one is this one. So can you tell me which one is the discrete time wavelet looks like? Actually, you remember this one. This one is a continuous wavelet, right? So why I use this is continuous, this different. This is a discrete time. Because continuous, we have scale, and we have time, right? And the scale is opposite with the frequency, right? And also we have a discrete time wavelet. So for the discrete time wavelet, we have level and the time. So I already discussed with you have the level, right? You have different level. So this is the implement the DWT is quite easy. You even don't need to know what's the filter, unless you want to know. But if you don't want to know, you can still run it. So you can see we use DWT very easily. So the last figure is CWT, you know, and here is I draw the DWT. Figure 2 is a DWT, right? So you can see I use what's the wavelet we use? Actually, we use Dubash 2, right? And we use 10 level. And this is a signal, right? And then we do the DWT. We do a several level of DWT, and then we implement and then draw the DWT figure, DWT transform. So this is a very normal way. And the DWT and have another very important property. Actually, in this subject, we will discuss with you about denoise of use DWT. So actually, in the MATLAB, they have not only for the code, they also have APP for the DWT. So you know APP. So you have if you have learned, for example, you just go to APP, and then you can search wavelet. So you have several wavelets. You have wavelet analyzer. You have wavelet signal denoiser. So this one is denoiser signal. And then we have also wireless wavelet form generation. So it's very powerful, right? So for example, we have we talking about this is a wavelet denoise. So you can load a signal. For example, I put this signal in. So this signal is the one I just generated. It's quite long, but because this one is no noise, but we can do the approximation, and we can see the coefficient of the denoise signal, denoise filter, and also we have so we can use this one to directly use. But in the assignment, I still hope you can use the normal code. So this APP you can try, and also have you see the live view? Is any group start to use live view to do the wavelet transform? Hi, Zhiqing. Hi, Mingnan. Hi, Mingnan. Hello. Because I cannot hear any feedback. I mean.
I can hear you.
You can hear me?
Yes, sir. It's clear.
Yeah. So how about your group? Is your group already use MATLAB and LabVIEW to do the DWT? Hello? If no one have some feedback, we look at this one. This is a wavelet toolbox. Actually, I'm talking about. This one is they can do the APP. They use wavelet APP. This use denoise. So you can see we can use different signal. I hope you can you already read this kind of video, and then you can ask me questions during the lecture time. And it seems the web is not very well connected. Have you tried this one? Is any group try this one? They can generate a signal and put a noise. They put some noise put a random noise, and then they generate a noise signal. And then they show you how to use MATLAB app to get rid of this noise. I think this is a very useful video. So you can see this noise signal. So how to use a wavelet, discrete time wavelet to denoise it. Hi, Jeffrey.
I can hear you, sir.
Yeah, you can hear me, right? Yeah.
Yeah.
We have some feedback. Yeah, actually, this is talking about the DWT, because last week we only left DWT, haven't been discussed. But
CWT, sir,
yeah, DWT we haven't discussed yet. Today we discuss DWT.
Yes, sir. Yeah, I already have the MATLAB code ready, sir.
Yeah, I know. Like, I have the previous year's video recording about the thing. But the only issue is, like, for the DWT, I want to student know how to use it first, and then can you explain the result. So this is, I put some videos very easy to learn. This use higher wavelet. So when you study the DWT, what's your difficulties you feel? Because I cannot get feedback from students. I just want to know what's your difficulties when you study.
So mine was to understand, like, every time I do DWT has to increase the levels. You can see the samples. If you, sir, you can see the samples have reduced from 1,000. It goes to each time. So then it was understanding how to combine the details and approximations.
Yeah. So they did some down sample, because
down sample. Yes, sir.
You have, for example, you have 1,000 sample. And then you need to down sample, because otherwise you have two parts. If two parts is the same number of samples, you will get double the sample. And actually, you after down sample, you still get the same sample size with the original one.
Yeah, once you reconstruct it, you would get the original.
Yeah, if you construct, and then you can recover the original one. So this one is this video give a very good explanation. But I still not encourage students to use the toolbox. Toolbox,
I would say.
Yeah, toolbox is just something like you just use a calculator and then do the things. Actually, you cannot understand the inside. So I still hope students can use normal code to implement CWT and DWT, and also denoise. Denoise is another very important thing. Actually, I use code to implement the denoise. Actually, it's I download from MATLAB. Oh, I need you to communicate with me. Otherwise, I feel like yeah.
Yes,
so
sir.
We will look at, for example, another DWT. This is a denoise. I think this is a denoise example. If I do this way. Oh, sorry. This is not. This is a denoise one. So this is a noise signal. This is an original signal. You can see. I want the student to understand
details and approximation.
Yeah, details and approximation. For example, for this one. For this one. We have a different level of details. So the first is this is original signal. We have a detail one, level one. Actually, we have a approximation one, level one, and the detail level one, right? So this is detail level one. So after we get the detail level one, we have another one is approximate level 1. The approximate level 1 to do a low pass and the high pass. The low pass, after low pass is approximate level 2. And after high pass is the detail level 2, right? So in that case, you can see the detail level 2 is lefted. And we continue. And we get approximate, we put the approximate level 2 to a high pass, low pass. We get level 3 low pass, low component signal, and all approximation, or we get level 3 details.
Yes, sir.
This is after the high pass. So we, in that case, recursively, we can detail 3, detail 4, detail 5. My question is how to reconstruct the original signal.
So to construct, you sum up all the, you take all the details and take the level 5 approximation.
Yeah, we also have level 4 approximation, right?
Level 5.
Yeah, level 5 approximation, and then we put we use a construction filter, use detail and detail level 5 and approximate level 5. We can construct approximation level 4, right?
Yes, sir.
Approximate level 4 and the detail level 4 together will construct approximation level 3. So this is a recursive procedure. Yeah, good. Your explanation, I think after discussion, we can easily understand this concept.
Yes, sir.
Yeah. So because today is very important. Like next week we will do the will stage 2. I think Aisha, can you hear me? Aisha is the only member currently is in the. Hi.
Yeah. I can hear you.
In the team 1. Yeah, you are in the first team. Hi, Aisha.
Yeah.
How about your team?
Yeah, so we have divided up our work and we have all the data that we needed, and accordingly we have started with our report.
Are you confident to give the presentation next week?
Presentation?
Yeah, because
I
next
think
week.
So like I haven't talked to my group mates yet, but we have divided up our work, and then we have a meeting after 2-3 days. Once we are done with everything, we'll just discuss what we are still left with and everything.
I didn't see you last week, you and Muhammad.
Yeah, I had an exam for other subjects. I couldn't make it.
Okay, so have you met Muhammad as well?
No, I haven't.
Yeah, Muhammad, I cannot see him for 2 weeks already.
Oh.
Is he still in the group? Hi.
Yeah, we are in same.
You still meet, right?
Yeah, we do have like online meetings.
Okay.
Yeah.
So have you is your group have any difficulties about stage 2?
No, not so far. No, we don't have.
So how do you learn? Because if you not come to the lecture, how do you learn?
No, but at least we have the recording, so I learn it afterwards. You know, like if I'm not able to attend it.
Oh, you have recording. I put the recording, right?
Yeah.
Okay. So in that case, for today, we will only discuss about discrete time wavelet. So I just discussed with Jeffrey about what's the difficult part of discrete time wavelet.
Okay.
Jeffrey told me is in regarding with different level of approximation and details, how to decompose the signal, how to construct a signal.
Okay.
So I think, have you learned wavelet before?
Sorry?
Have you ever learned wavelet before?
Wavelets?
Yeah.
I'm a little bit aware of it. I just need a revision, but yeah, I have read before.
Okay, you learn from these subjects, or you learn from previous study?
Previous, like when I was in my bachelor's.
Oh, yeah, that's good. In that case, you have learned that. That's good. So, in that case, I continue the discussion about the wavelet, discrete time wavelet. So I ask maybe Jeffrey, another very interesting question is like because for discrete time wavelet, we use filter bank to implement, right?
Yes, sir.
Yeah. So for the filter bank, we have a low pass and high pass.
High pass, yes, sir.
We have 2 low pass, 2 high pass.
Yes,
right?
sir.
Yeah. For the because for the wavelet, we have the wavelet. What kind of wavelet we select? For example, sometimes we use Dubash wavelet. We use Mexican height filter.
Yes, sir.
And with a Haro filter. So how to implement? Because you just design a low pass, high pass filter, right? So how to for example, I want to implement Haro filter, a Haro wavelet. So how to implement? Where's the trick?
So we got to understand that the details are actually the low pass, and the approximations are the high part of the signal.
Yeah.
And when we do that, we can choose Bior or something and pass that. When we combine it, when we reconstruct the signal, we take all the low and the approximation, we combine them, and then we send it through the wavelet. That's, let's say, for Bior 3.5 or whatever it is, and then we can get that. Yeah.
Actually, these coefficients of the filter determine what kind of wavelet you selected.
So that's the details. The details gives us the low pass part of it.
Another interesting question is for the filter is FIR or IR filter in the filter bank. We use FIR filter to implement. So this is a very interesting topic. Actually, if you because for application point of view, it's very easy. It's just like we can use MATLAB to draw to help you to do the denoise or to do the analysis. But if you want to do the research, you need to know how to design the filter bank. Actually, this filter bank is very important. It will determine what kind of wavelet you use. Yeah. So maybe Jeffrey, time is running okay. So you can explain from your point of view how to use LabVIEW and MATLAB to implement DWT, and also how to do the denoise.
Yeah, I can show. I'll share my screen.
And I hope students can directly ask questions during your presentation, and also during my presentation. We can ask a question each other to make things more interesting. Otherwise, just you or just me to explain is very not interactive.
Yeah, I'll share my screen.
Hi, Rina. You are connected.
Yeah. Yeah. So can I share my screen?
Yes. Yes.
Yeah, I can share my screen. Can you all see my screen?
Yeah, I can see your screen. Yeah.
Yeah. So can you see MATLAB, or are you seeing the Chrome?
Yeah, I can see your MATLAB code.
Okay, cool. So you don't have to do this much of code. I'm showing you this code because in MATLAB, you just have to use this function called WD noise. But if you just use this function, you won't know what's happening in the background, like what actually happens. So that's why I've written this many lines of code so that you understand actually what happens. So now the first thing that we got to do is that we got to decompose the signal, okay? We got to decompose the signal. So the decomposed value is called wave deck, okay? Wave deck is how you decompose the signal. And when you use that, when you use the decomposed value, you should put your filter, the signal, the actual signal, okay? The next number is the levels. What's the number of levels that you want to do for your how many levels do you want to break down your signal into? So to break that down, we take number 5. So I'm just putting 5. So if I can put 7 or 5, but for now I'm putting 5. And I'm choosing the wavelet has Bio 3.1. Okay, but that Bio 3.1 is chosen based on my signal. So for your signal, it could be different. So I want you to have a look around, look at different literatures and see what type of wavelets do they use for EEG, EMG, or ECG. So you'll have a better understanding of why we use certain types of wavelet, okay? Now, once you do that, the next thing is to break down the signal. Now, we want to see all these levels, right? We want to see these different 5 levels. So then we try to extract the detailed coefficients, okay? 5 levels of detailed coefficients. So we need 5 levels, right? So we'll have 5 outputs. So CD1, so CD2, CD3, CD4, CD5. So those are the 5 levels of outputs that you're going to see, okay? Now, when you see that this one has an input, okay, C and L, okay, that's we got it from wave deck, and then we put all the levels. So let's say if we have 10, then it will be, let's say if I had 7, then I would put 5, 6, 7. But since I'm only going with 5, I'm going to put 5. It's going to be the same here as well. CD1, CD2, CD3, CD4, CD5. Okay. Remember, this is to decompose. This will help us to extract the detailed coefficients. That's what it does. It extracts the coefficients for us up to 5 levels. Okay, up to 5 levels. Next is the approximation. That's a function of MATLAB, approximation coefficient. So it extracts the approximate coefficient. Remember, it only extracts the 5th level, not all the 1, 2, 3, 4, 5. Okay, I'll show you that in a while. It only extracts the 5th level. Okay, so let's see how it happens. So what I've done, I've made a subplot of D1, D2, D3, D4, D5. So there are 5 levels of. Let me just run it. Can you all see my?
Yeah, I can see.
Screen? So can you see the EMGs? Can you see the EMG signal?
Yeah, this is 5 level. 5 level.
Yes, sir.
Detail. 5 level of detail. So your approximation you have to show is that this is a.
This is only details. I'll show this EMG. Yes.
Yeah. So they have the same. You can see they have a similar length.
Yeah. So you can see that as I go down the levels, it's getting downsampled as well.
Yeah.
Okay. So 10 to the power.
Sorry, these are not a similar length. They are half. Right. Each time is half.
Yeah. It's each time it's half. Yes, sir. So you can see that it's 14,000, 7,000, 3,500. If I add another level, it will go 1,250. It will go even.
When you construction, you need another half part. A half is for loss approximation.
Yeah, so I'll show you the approximation also now.
Yeah, approximation will. Normally, the approximation is to have noise. Have signal.
Yeah. Actually, so I'll show you. I can
noise.
Yeah, if I plot the
approximation.
If I plot A1, that's my approximation. Okay, you can see the approximation. Yeah, so you can see this is approximation at A5.
This is A5.
Yeah, A5 approximation, not the details.
A5 have around 3,000 data.
500. Right? Yeah, that's because it's level 5.
Level 5. So you look at your detail 5.
Yeah, so I'll just put that. Yeah, I'll just put that into.
Actually, they also should be around 3,000.
Yeah, it's 3,500. Yes, that's correct. So wait, I'll show you that.
Actually, in the workspace, you can see that.
Oh, sorry.
CD5 is 3,127 times 1.
Yeah, I can show you A5 title A1. Okay. I would recommend you to go through this way so you understand exactly what's happening. If you go the easy way, sometimes you might not understand each and every step.
Yeah.
So
yeah.
let
So
me.
This is good. I think your material is
So
good.
this is to understand how step by step it happens. Why we do that? Okay. See, I'll show you these. Can you see my graph now? Can you see
Yeah.
D1, D2, D3, D4, D5, and A1? See, A1 is also 3000, but that's at level 5. So it's similar. You can see that it is similar to the number of, it is also damn sample.
This is A5, right?
Yes, A5. A5, yeah, sorry. Yeah, I've not named it correctly. It's A5.
It's A5, yeah.
Yeah, so I can show you how it looks if I reduce the number. So let me change A to like level 2. I'll show you it, and if I run it. Wait a second, I'll just close this. I'll just close this. And yeah, so now you can see this is A is level, see A is level 2. So this is A2 and see D2. See, it's very similar now. This is actually A2. See, you can see the sample, it's 2.5, see?
Yeah.
So that's what, you take the final level of your approximation. So that's how you take your different levels of approximation. So let me change that back to 5 so that we are all on the same page. Yeah.
So students should understand, actually, this is a very good example, like what's the approximation level and what's the detail level. So normally details is actually the code details actually is similar as noise. Actually the signal, you know, like signal is often in the slow, is in the low frequencies part.
Yeah.
So, but you can have a different level of approximation. So this is a very good or very important aspect of DWT.
So this is the last level of the approximation, okay? So now this part is called decompositions of details. So this is just to see how the decomposition is done. This is just the decomposition part. Everyone good till here? Any doubts? Happy to answer if you have. Yeah, okay.
Yeah, if you have any, you can continue. And basically we need to give a student the skill how to do the DWT and how to explain the DWT. Probably you will show them how to use DWT to do the denoise.
Yeah, I'll show. I have that as well. I have that as well.
Yeah, and then
So now we have the reconstruction. So now we deconstructed the signal, right?
Yeah.
So in MATLAB, you have a single code that can do all of it for you. You wouldn't know. This is just to understand how it works if you're doing so. When you do reconstruction, there's something called WRCOEF. Okay. Now this is type is D. The D means details. So you're reconstructing the details. Okay. You're reconstructing the details. So D is details. Okay. So it takes details of 1, 2, 3, 4, 5. Okay. That's D. And then this is approximation. That's reconstruction. Okay. Reconstruction and at level 5. So if we have to plot it, I'll again plot this at level 6, so you'll understand. So 6. I'm putting it 6 because I have 6 plots. 6. Okay. So now if I have to plot this, you can see now the sample sizes are not as small because this is a reconstruction in those levels. Can you see that? If I've reconstructed at level 1, level 2, level 3, level 4, level 5, level 4.
So I want to ask which level have the lowest number of samples?
At the highest level. So if you have the fifth level will have the lowest number of samples. So as you increase the levels, your samples will get halved.
Yeah, you lower your sample. lower your level, and you will get a high number of samples.
Yes. So let me just plot this again. Yeah. So you can see when you construct it back, you can see the sample size are low. So, but you can see how the baseline. Can you see the baseline? How it's removed the baseline noise? It's much thinner. Yeah. You can see level 1. See that? And at level 0. But what happens if you keep on increasing it? If you keep increasing your levels, ultimately you will lose the signal itself. So you can't put very high number of levels itself. So you got to be very careful. So how do we combine the signal? So when you denoise a signal, it's actually the combination of all those details and the last approximation. So when you do that, it's actually the combination. I'll show you this. It's a combination of A5, that's the approximation, level 5, and all the details. So this would how the signal actually looks like when you do it. But instead of this, you have a MATLAB functions called WDenoise. See that? Okay. Now this one, you can take your filter. Okay. Yeah. C1 filter. So I put number of levels 5, right? 5 wavelet bio 3.1. Okay. Now so you can use this function called WDenoise instead of this. So I just showed you these two so that you understand how it actually happens. This function does that, both of those things for you. Remember, this function does this part and this part for you. So let's run this.
Jeffrey, I have another suggestion. Your signal, you use EMG signal.
Yes,
so
sir.
EMG basically, you don't have a very good low frequency component. Probably if you use generated, the artificial signal, for example, sine signal plus noise, and the student will be more close. But this one also okay, but it's a little bit, student maybe see all the same.
Because if you see the baseline, can you see the baseline in the original signal?
Yeah.
And there's, when you see the denoise signal, in the denoise signal, the baseline is much more reduced.
Yeah.
Yeah, so I've put them together side by side. So you can see that the green one is the original signal. Can you see the green that's overlapping? And the orange is the denoise signal. So you can see that the baseline has significantly reduced by doing that. So if you actually take your ECG, let's say if you do an ECG signal, if you do an ECG signal, you should see a much more clearer output. Yeah, so you can use that function to actually denoise it. So you can see that how very thick it is. But if you see it, it's much more significant because you can see that these lines over here are much more thinner here.
Hi, Jeffrey.
This is, yeah.
Yeah, it's good. I think you can use this one. And if it's possible, you can try use a sine plus noise. Probably that will be, student will be more.
Yes, sir.
Yeah, but anyway, you continue and until this finish, and then you can try. You can try to.
Yeah. So what I want you guys to do in lab is actually plot these two. I want you to plot. I don't want you to just use the denoise, this function itself, because this function, if you use this function, you wouldn't know what's happening in the background. So I want you to separate approximations and details and have a look at it. Okay. So like what I showed you, separate up, have your detail, decompose the signal, okay, deconstruct the signal, and then, and I also want you to reconstruct the signal. So how do you reconstruct the signal? You reconstruct the signal using the details and the approximations. Cool. Then finally, you can use DWNoise just to test your, and you can test out your final signal, your denoise signal. Okay, now I want to show you something else. So I'll show you something similar to, give me a minute. I'll show you in a lab view with another signal. So if it makes a little more sense, I'll show you another signal. Give me a minute. So in your lab view, can you all see my lab view?
Cannot see. Yeah, we can see your lab view now.
So in lab view, the function is called wavelet denoise. Okay. I want you to do a little bit of search on this so that you can. I'm just searching for the.